When the volcano Eyjafjallajökull erupted in Iceland in 2010, it resulted in widespread closure of European airspace. This was because of the policy of aviation authorities that aircraft should avoid ash clouds because of the damage that could be done to engines and the resultant chance of engine failure. There have been more than 250 events of ash being encountered by aircraft in the last 30 years, so it is important to understand what happens when this occurs. When ash is ingested by engines, it may stick, bounce, or spread on impact with engine surfaces, and the likelihood of each outcome depends on the impact velocity, impact angle, and particle rheology and surface properties of the engine surfaces themselves. This picture here on the left, you can see the different ranges of outcomes of droplet impact on surfaces, going from gentle deposition to complete rebound of the droplet. Ash sticking to jet engine surfaces, as shown on this picture here on the bottom right, is a particular problem, as it can block air ducts, restricting airflow and making an engine failure more likely to occur. When doing experiments looking at this problem, it is important that they are appropriately scaled, so that the behaviour of ash inside a jet engine can be accurately captured. So far, data from previous experiments has been analysed to determine whether they are appropriately scaled to capture the behaviour of volcanic ash in jet engines. To do this, we recast the physical variables as dimensionless numbers, more specifically the Weber and Auger-Sorger number. We find that the dimensionless numbers calculated for the experiments, represented by these points on the graph here, are very different to those calculated for the actual case of volcanic ash in a jet engine, represented by this rectangle on the plot here. This suggests that previous laboratory experiments have not accurately replicated the real behaviour of volcanic ash in a jet engine.